Okay. So we were discussing the gravitational attraction. Do you have any questions to ask before we begin? Now we had seen that we started with Kepler's laws. We had the Kepler's first law, then the second law. We discussed that the Kepler's second law just implied that for any point on the orbit of the planet, this product, the distance from the sun times the speed of the planet times sine of the angle between these two vectors is constant. We will study conservation laws in a few chapters. This is one example of a conservation law. It is a product of things which change in time. It's a combination of things which change in time, but this combination itself doesn't change in time. Although r changes with time, v changes with time, and theta changes with time, this product is always constant, no matter where you are on the orbit. In particular, we had seen that for circular orbits, this meant that the planet is doing uniform circular motion, because theta was 90 degrees for a circular orbit, r is constant, so the speed has to be constant. And then we had the Kepler's third law, which just stated that this ratio, t squared over s cubed, was the same for all planets. And then we saw that this implied that the force acting on the planet multiplied by its distance from the sun is constant for all planets. This product doesn't change from planet to planet. It mainly means that the force acting on the planets goes as 1 over r squared, so that when we multiply with r squared, we obtain a constant. And then Newton just generalized it to any masses, not just planets. For Kepler, it was just for the planets. But then Newton said that it was for any object with mass, they act with a force on each other. This force is proportional to the masses of the objects, inversely proportional with the square of the distance, and the proportionality constant we call the Newton's constant, which is given by this number over here. It's quite a small number. And in fact, it's one of the puzzles of modern physics. Why is the gravity so weak? Now, compared to electromagnetic force, for example, it is 40 orders of magnitude weaker. If you just take 2 protons and compare their gravitational attraction to their electrostatic repulsion, the ratio is 1 followed by 40 zeros. And since force is a vector, we have to specify its direction also. And this gravitational attraction always points from one mass to the other mass. If you calculate the force acting on mass 1 due to mass 2, it is equal to the Newton's constant times the product of the forces of the masses divided by the square of the distance between them, and it is in the direction pointing from the first mass towards the second mass. And we said that, okay, if this is the force acting on any mass on the surface of the Earth in particular, so we had already seen that for any object on the surface of the Earth, the force can be, its weight can be written as its mass times the universal gravitational acceleration. But from this universal gravitational attraction, we can also write it in this form. Well, this square is over here. Newton's constant times the product of the masses divided by the radius of the Earth. Since we are on the surface of the Earth, it is the radius of the Earth. So this gravitational acceleration, the universal gravitational acceleration for any mass on the surface of the Earth, which we know that it is around 9.8 meters per second squared, has to be given by this expression over here. Now, one interesting thing about this expression over here is that this number we know, it is 9.8 meters per second squared. This number we do not know. The radius of the Earth we know. You know how to measure the radius of the Earth from your homeworks. The Newton's constant, we had discussed the Cavendish experiment. So using Cavendish experiment, we can measure this Newton's constant. The only unknown in this equation is the mass of the Earth. So this would give us the mass of the Earth. So that was all we did on Thursday. Now, any questions? Now, I just would like to make a reminder to you. Okay, we are more or less discussing everything in the book, but it's just more or less, not everything written in your book. But you are responsible for the material in your book also. Now, in your book, I came to realize that not many of you looked at the end of the book where you have the appendices, you have the mathematical formulas, derivatives and integrals. Well, this mathematical formulas appendix also includes definitions of the logarithm and the properties of the logarithm. Well, more on dimensional analysis. We didn't do much on that except that in the first few weeks. And this appendix D we will be discussing today, but you can also look through the book. Just remember to read your book. Now, we had discussed the G. This is Earth. You are on the surface of the Earth, let's say somewhere over here, and you measure the value of G. Now, the value of G that you measure will be different from the value of G that somebody else measures, let's say here. Now, how do you measure the G? You just take a scale, you measure their weight, you take a known mass, and you measure the weight, divide by its mass, and this will be your G. Or you can just drop an object and look at its acceleration. It will be again the G. But the G measured by different people will be different. There are various reasons for that. The first one is that the shape of the Earth is not uniform. It is more or less like this. Now, this is a bit exaggerated. But if you are at top, you are closer to the center. The radius of the Earth at the polar regions is much smaller than the radius of the Earth at equilateral regions. So you are further away from the center at the equator. You are much closer to the center at the poles. So this will mean that the G will be different depending on whether you are over there or over here. Furthermore, if you have a large mountain over here, the mountain will also exert a gravitational attraction to you. So the G that you measure at this point will not be exactly towards the center of the Earth, but it will be a bit shifted due to this mountain. Mass density is not uniform. Well, you can think that, okay, here you might have a reservoir of water, underground water. Water on the average has a lower mass density than the rock, than the Earth on the average. So if you measure G here, you will get a smaller value than if you would measure, I don't know, here with some, this is water, this is iron. If you have some iron deposit over here, since iron has a much larger mass density, if you measure the G here, you will get a larger value of G. There are also caves. If there is a cave, well, it's filled with air, which has a much lower mass density, so you will get a smaller value of G. Well, the differences will be just 1 part in 10 to the 7. So 1 over 1 followed by 7 zeros. But nevertheless, it is measurable. And in fact, it is one of the ways which we use to look for iron deposits, water, underground oil. At least it is one of the hints. Well, there's also the problem of rotation. Earth is rotating. So what it means is, if you are, let's say here, Earth, let's say it's rotating around this axis, and you compare someone here, you put him on a scale, and someone on the equator, you put him on a scale, and measure the weight of the person. Now, what will happen is, there will be mg pointing in this direction. In this case, it will be, let's say, mgp in the r hat direction. Mg equator in the minus r hat direction. They are both towards the center. Now, of course, the scale will apply a normal force. This is the normal force on the poles, the normal force on the equator. Sorry, this is G. Well, if you just ignore all the other effects, the shape of the Earth, the mass density of the Earth, just ignore all the effects. In that case, the gravitational pull at the poles and the gravitational pull at the equator will be the same. But if you measure your weight, which will be nothing but the magnitude of these normal forces, on the pole, NP plus minus mg r hat should be equal to 0, because that mass over there, that person over there, is not accelerating. So NP, the magnitude, will be just mg. So if you define the gravitational acceleration at the pole, the measured gravitational acceleration on the pole, as the normal force, the weight measured by the scale divided by the mass, this will be equal to g. Whereas if you look at the equator, we have the normal force at the equator plus minus mg r hat. But now the Earth, since Earth is rotating, the mass over here is accelerating with an acceleration pointing towards the center of the Earth. So this should be equal to mass times the acceleration, which we know that it is v squared over the radius of the Earth in the minus r hat direction. This should be, these two should be equal. But this tells me that the magnitude of the normal force, or the normal force, should be mg minus v squared over the radius of the Earth in the r hat direction. I just moved this number over here. So the gravitational acceleration that you measure on the equator would be just this number over here, g minus v squared over the radius of the Earth, which is less than the gravitational acceleration that you would measure at the poles. So so this this g, although we just quote a single number, 9.8 meters per second squared, it does change from point to point on the surface of the Earth, depending on where you are. Now, another thing, you don't have to go to the equator. You can just look at an arbitrary point over here. For an arbitrary point over here, you have the gravitational attraction pointing towards the center, the normal force pointing outward, and these two should combine to give an acceleration which is pointing towards this point over here. Because that point itself is also making a uniform circular motion around this point. So the object over here will be accelerating, and hence the g that you will measure over there will be different from this value. It should be g minus v squared over re times sine of the longitude you are at. So if you are at 0 degrees, then this is the value. If you are at 90 degrees, this is your value. If you are at 0 degrees, then this should be your value, g. So it changes depending on your latitude also. Not only depending on the shape of the Earth, the rotation of the Earth, or the mass density of the Earth, but also depending on where you are, on which latitude you are. Now, there was one point that I was kind of cheating. We were using this gravitational attraction law for planets, which are large objects, and the sun, which is also a large object. So we have the sun over here. We have the Earth somewhere over here. And we said that this gravitational attraction between the two is equal to the Newton's constant, mass of the sun, mass of the Earth, divided by the distance between them, pointing from one to the other one. But what is this distance? Is it the distance from the centers? Well, that is the right answer. But why not take, I don't know, this distance from the closest point on the sun to the closest point on the Earth? Why not that distance? Yes? Does it work? Is it true? We are thinking like that, that is true, but is it true? But is it? Have you seen a proof of it? Well, why not? I can imagine. Okay, I can imagine the sun as a point at this point. Why not? Why sun? Why? Well, that is the right answer. We know that, and we will prove that. But why do you think it is more logical, the center? Why is the center of mass more logical? Well, let me tell you this one. Let's not take the sphere, but let's just imagine an asteroid of an arbitrary shape. In this case, the center of mass, taking the center of mass as the point of concentration of all the mass doesn't work. In this case, it doesn't work. Isn't? In a sense, I mean, do you mean that if we take, for example, for the sun, if we consider this point and this point, this will have a stronger pull, this will have a weaker pull, so that the sum will be kind of a pull from here. That is what happens. But that is somewhat what happens. Let's be more precise. We have to be more precise. And as physicists, okay, you can have an idea. You can just do vague arguments saying that, okay, it is more logical to this, that these two forces sum up to give a force as if it's acting from this point. But at the end of the day, that gives you your strategy. I mean, your general idea gives you the strategy, how you will attack this problem. But then, eventually, you will have to give a precise proof of what you are claiming. Now, let's do that. Now, there are a few things we have to do, we have to discuss. First, okay, the law that we had written, this one, the F is equal to the Newton's constant times the product of the masses divided by r squared. It is strictly valid only for point masses. So for extended objects, well, if we have more than one object, let's see. If we have more than one mass, M1, M2, M3, and so on, Mi, you can talk about the force acting on this mass over here. Well, we know that there is a force due to this mass 1. Let's call it F1. There is a force due to this mass 2, F2. There is a force due to this Mi. Let's call it Fi. In Newton theory at least, the force, the gravitational attraction that this mass M feels is sum of all these forces. I is 1 to n. If we have n other objects, then the force acting on my mass M will be just the sum of the forces that each one would act in the absence of the others. So if there is only this mass 1 M1, but there is no M2, M3, Mi, there is a force F1. Now when I put this M2, M3 and all the other masses, the force that this exerts on this mass doesn't change. That is an assumption. In fact, it works in Newton theory, but it doesn't work in general relativity. In general relativity, this assumption is wrong. But since we will be, in this semester at least, we will be dealing mainly with the Newton theory, so we will just use this fact. Now, the reason why it doesn't work in general relativity is that if you consider the forces, the force is Newton's constant, M1, M2 divided by r squared in some direction. The force depends on the masses only. Now, in general relativity, this gravitational attraction is not created by the masses, it is created by the energy of the system. So, and you know the famous formula. If you have a mass, it has an energy, corresponding energy. So it is this energy that should appear here in Einstein theory. But if you have such a system, okay, this mass here has an energy. If you put a second mass, this mass also has an energy, but there's also their mutual gravitational interaction energy. That additional energy also creates a force. So here, in between these two, you have gravitational energy. So this will also create some gravitational attraction. So the force that this will feel will be more than what this would create without the other one plus this one. What this would create in the absence. It will be larger than F1 plus F3 due to this gravitational energy in between. But that is something just to keep in mind. We will not be studying general relativity. We will stick with this superposition principle, so-called superposition principle. This is what we call the superposition principle. So we are just superposing different forces as if they were independent. And in this case, they are independent. Now, to prove that we can take the sun as a point mass right at its center of mass, now the strategy we will take will be, if you have this is sun. It's a solid sphere. Not solid one, but filled sphere. So we can imagine that it is made up of very thin shells. So to calculate the gravitational attraction of the sun, first I need to calculate the gravitational attraction of each one of these shells. Now to calculate this gravitational attraction of each one of these shells, well, the sun is a sum of these shells. I can just take this, my empty ball, cut it into very thin slices. So these are my slices. Now, each one of these slices is very thin. It's almost a line. Each one of these slices is in fact a ring in itself. Almost a ring. Infinitesimally narrow ring. So, in order to calculate the mass of the gravitational attraction caused by the sun, I can start with the ring. So, that is what we will study here first. So, we have a ring of mass with radius capital R, and we put a mass at a distance L from the center. Now, when I'm cutting these shells, okay, if I put my mass here, this is the line connecting my point mass to the center of the sun. This is my point mass. This is the line connecting it to the center of the sun. I will just imagine I'm just cutting these slices such that they are perpendicular. The slices are perpendicular to this line. So it is just that case over here. So I'm putting my mass here. I consider the line that goes through the center of the ring, and it's perpendicular to the plane of the ring, perpendicular to this plane. I put my mass here and ask for what is the gravitational force that this mass m over here feels. So this is our first question. Now, well, just as we did here, we had a large mass, we divided it into very small masses, we further divided it into even smaller masses, each one giving a ring. Now this ring I can just divide into very small arcs. These are all the arcs I have. I have one arc over here and another arc over here. So I have, so this is my ring. This is my ring. Oh, without this. This is my ring. So I just divide it into very small arcs. So the ring is just the sum of all these very small arcs. This is what I am imagining now. Now, the system is quite symmetric in the sense that if I take this piece over here in one end. Then in the diagonally opposite end, there is another very small piece that has the same mass. Now, so this mass here will create a force in this direction. Let's call it F. This very small arc will create a force in this direction. Let's call it F prime. Now the masses are equal. I'm just assuming that I'm dividing my whole ring into very small arcs of equal length. So each arc has the same mass. So each arc has the same mass. Well, since I'm right at this on a line which goes through the center of the ring and perpendicular to the plane, any point on the ring, the distance of any point on the ring from my mass is the same. So if this distance here is, I denote it by d, then this distance itself is also d. So if you just imagine it, I have this ring. I'm at such a point. Now the distance of this mass from this point and from this point, they are equal. So if you just imagine the line going from the top, my mass, to the ring, and imagine that you are rotating that line, you just get a straight cone. So if you, this is my ring. If you put it over here, you just imagine this line, all the lines that connect my point to the edges of my ring, this is my cone with the so-called apex angle, theta. This angle theta is the same whether I take this point, or this point. It's the same angle theta. So this angle theta. Now let's write these forces, F. Okay, let me choose some coordinate axis. This, let's call it the z-axis. This the x-axis. Now the F, the force created by this mass over here, let us call it some delta m. So this arc has mass delta m also. They have the same mass. So F will be Gn, m, which is the mass of my point here, times delta m divided by d squared. This is the magnitude of the force. It has a component in the x direction, so which is given by sine theta in the x direction, plus Gn m delta m over d squared times cosine theta in the minus z direction. This is my F, the force created by this mass over here. Now, if I consider the other mass, this mass, F prime, it also makes an angle theta. It has a component along the z direction which is equal to this one. Well, the magnitude is equal anyway. So it is the cosine theta in the minus z direction. So this is exactly the same. But if you look at the component of this force in the x direction, it is given by the sine of this angle, but it is in the minus x direction. So it is all this thing in the minus x direction. Now what happens is if you want to calculate the total force created by the ring, you have to sum all the forces created by each one of these small arcs. So for each mass, for each arc, there is a corresponding arc in the opposite side of the center, such that the x component of the force is in the opposite direction, but the z component is in the same direction. So when you sum them up, this will cancel this one. So the resultant net force created by the ring will be in the minus z direction, because all these arcs will create a component of force in the minus z direction, which will add up. well, they will also create a force in the x-z direction, which will cancel. So that is something that we already know. So we can say in general that the force will be in the minus z direction. So we can just ignore all other components of the forces. Already we have proven that the forces in other direction, in the perpendicular direction to z, they will cancel. We will be left with a component only along the z direction. So I have this very small force, very small mass. It creates a force in the minus z direction given by this expression. It is contribution to the net force in the z direction. It is given by Gn, the product of the masses, divided by d squared times cosine theta. Of course, it is with a minus sign because it's in the minus z direction. Now, if I want to calculate the total force acting on my mass, it is just sum of all the forces of all these points, or almost point arcs. So the total force is the sum of these Fz's. Of course, in the limit that the length of these arcs goes to 0. Now, you should already be familiar with the fact that this is our integral. So you will end up having an expression for the force as an integral over the ring. But we will not even need that integral. Let us write this explicitly. Gn m delta m over d squared times cosine theta. I'm summing over all these very small masses. Remember, I had this ring. I divided into very small arcs. Each arc has a mass delta m. Now, Gn is just a constant. M is a constant. It doesn't change from delta m to delta m. Cosine theta is itself a constant, because whether I take this point or this point or this point, this angle that this vertical line makes with the line connecting my mass m to the point on the ring, it is always theta, it is constant. So I can take all of them out of my summation sign. Now what I have now is I'm just summing the masses of each one of these arcs. I'm summing them over all the arcs. But that will give me the total mass of my ring. Over d squared cosine theta. I have a minus sign, which I had forgotten. I have a minus sign over here, so I have to carry it along. So this is the net force acting on my mass m over here. So if I had asked you what is the net force acting on the ring, what would you do? What would you say? Okay, let me ask you this. The net force acting on the ring, would it be smaller than this, larger than this, or equal to this? Okay, who says larger? Hands. Who says smaller? Who says equal? Who is sleeping? It will be equal. They are just action-reaction pairs, Newton's third law. It already tells us that if the ring is acting with this force on my mass m, then my mass m should be acting on my ring with a force which has the same magnitude, but it has the opposite direction. Well, I can just re-express this a bit more. What I would like to do is, well, I know L and I know the radius of my ring, so I would like to express everything in terms of those numbers. So this is my ring. This is the ring. I'm just looking at straight from the side. So this is the central point. This is my mass over here. So this is my D. This is, let me see, this is my L. And this is my angle theta. And this is the radius of my ring. Now I would like to express everything in terms of the radius of the ring and my distance from the plane of the ring. If you look at here, well, cosine theta, well, let's start with D. D, well, it's just, this is a right triangle. Since it's a right triangle, I know that D is R squared plus L squared to the power 1/2. And cosine theta, this is equal to L over D, L over R squared plus L squared to the power 1/2. If I just substitute them over here, I know that the total force acting on my mass minus the Newton's constant, capital M. Now let me. Minus the Newton's constant, capital M, L over R squared plus L squared to the power 3/2 in the z-hat direction. This is the total force acting on my mass. Okay, now we have our result. So does our result make sense? This is something that you should always ask yourself. Does it look meaningful? Now, to see whether it has sense or not, you can just test it using certain limits. So which limits do you think would be interesting? Okay, let me tell you one of the limits that would be interesting, the limit when the radius of the ring goes to 0. Because if the radius of the ring goes to 0, it just becomes a point mass. So we know the force between 2 point masses. If you just take R equal to 0, then we have L divided by L cubed. That is 1 over L squared. So the force acting between this point mass and another point mass has the magnitude, Newton's constant, the product of the masses divided by the distance between them squared. So that is the law that we started with. That is one of the interesting limits. And we know that we had already seen that in that limit, our result does make sense. It just matches with something we know already. When we take a limit and convert our problem to a system that we already know, the problem of the gravitational attraction between 2 points, we already get our previous results. So what other limits do you think are interesting that we can compare? Anything? Okay, what about L equal to 0? If we study this system in the limiting case when L goes to 0, that is, we have our mass, we just position it right at the center of the ring. We predict that the force is exactly equal to 0. So do you think that makes sense? There's no gravitational attraction, there's no gravitational force acting on my mass? Why? Okay. Okay. It will cancel. Yeah, exactly. So if you put a mass over here, there is one part of the ring right here which will attract it in that direction. There is another part of the ring here which will attract it in the opposite direction with equal magnitude. So the sum will be 0. It's just like in this example, we had shown that the components along the x direction, it just cancels. It is the same story here. The only component is along the x direction, if you are sitting right at the center of the ring. So the only component is along the x direction, so it just cancels. So there, yes. No, we are assuming that we are taking the limit that r goes to 0, but the capital mass m is finite. By increasing the density. Okay, is this realistic? This problem. This problem is not realistic. I mean, we never have point masses. We never have masses in the shape of a ring. Well, problem. Half of you probably have rings, but you don't worry about the gravitational attraction of that ring. So, I mean, this is not a realistic problem in itself. But remember, eventually we are trying to head from this ring to the sphere. Then we will have some more realistic problems. Now, in this example, what I am assuming is that I am assuming that the mass of the ring is constant and changing the r. It just means I'm changing the density of the ring, if you like. If I have a smaller ring, then it will have a larger density. If I have a larger ring, it will have a smaller density. Okay, so there is one more limit which we can discuss. Infinity, yes. Oops, sorry. Well, the other limit is L goes to infinity. So what happens in that limit? Well, we don't even need to go that far away. Suppose we are very far away, but we can still see the ring. Let's see. So, do you have some eraser? At the back seat, yes. Yeah. One of you. Any eraser? Silginiz var mı? Anything small? Do you have any rings? Yes. Now look at that thing, whatever that is. It looks like a point, no? I mean, not for those of you over there, but for us at this corner of the room, that already looks like a point. So if I'm very far away from this ring, and I'm measuring the gravitational attraction of the ring will look like a point. So in that limit, when L is very large, but still finite, we know that it should again reduce to the limit when I have 2 point masses attracting each other. If you look at the stars, let's say, stars, they are huge objects. But at night, if you look at the sky and look at the stars, they just look like points to you. So the gravitational attraction should also be as if they were just point masses. Now let's take the limit that L is much larger than the radius of the ring. If L is much larger than the radius of the ring, then we can just ignore this r squared term compared to this L squared term. Let's just imagine that L is 1,000 kilometers and r is just 1 meter. It is just 1,000 squared plus 0.00 many zeros, 0.1, many zeros, 1. So compared to 1,000 squared, that is just negligible. If you ignore that, r squared, then you have the product of the masses times the distance from the ring divided by L squared raised to the power 3/2. Well, that is L cubed. We are again back to the case that the force is the Newton's constant times the product of the masses divided by L squared. That is the force between 2 point masses, as it should. So the limits do make sense. So probably this is the right answer. So we already have the answer for this one. Now let's take a step further and go to the shell, spherical shell. That is after the break, and so you will have some time to wake up, because that will make you sleep even more.